Hey everyone, I hope you're doing well. It's Dr. Fraser again, and we are now going to talk about interactions of two numerical variables. So let's set the scene. An educational researcher is trying to analyze the factors influencing the applicant pool for a Master of Science in Accounting program at medium-sized universities in the United States. So schools smaller than WVU, schools more like the size of Marshall or Fairmont State. Turns out that two important factors are marketing expenses of the business school and the percentage of alumni who are employed 3 months after graduation. So the marketing underscore MSA dataset in the Chapter 7 datasets file includes data on the number of applications received, marketing expenses in thousands of dollars, and the percentage of graduates employed within 3 months of graduation. Before we get started, you want to make sure that you've imported and attached your data set in R. As you can see on my screen, I have my data imported, my applicants, the marketing expenditures in thousands of dollars, as well as the percentage of graduates employed within 3 months of graduation. So I've already pulled it in, and you can see the code that was used when I imported the data set. Now I'm going to attach it. And remember, we like to attach files to our working directory so we can just refer directly to the variables. We don't have to prefix the variable every time we use it with the name of the data set. So I'm going to type attach marketing underscore MSA. And now I can call on the individual variables. I don't need to worry about typing marketing underscore MSA $ before I type in the name of every variable. So first, let's estimate the effect of marketing expenditures and the percent of graduates employed on the number of applicants. And we'll call this Model 1. Model 1. We'll use the LM function, our linear regression function, and we're looking to predict the applicants. That's a tilde, not an assignment arrow. Applicants being our dependent variable. And now we're going to add our independent variables to the model, which are marketing and employed. I'll hit enter, and now we see under our environment pane that model 1 is created. It is a real thing. And we can use the summary command to take a peek at what model 1 looks like. So here we see that all of our variables are quite significant. Our p-values for both marketing and employed are very, very small. And then we can look towards the bottom of the output and see the overall evaluation of the model. Adjusted R-squared of 0.7254 is pretty darn good. And we see the p-value is extremely small, suggesting that this is a very significant model. So that's pretty exciting. So assuming a marketing expense of $80,000, let's predict the number of applications received if 50% of graduates are employed within 3 months. And to do this, we're going to first create a vector out of our coefficients. So coefs1 is the vector we're going to create, and it is going to be the coefficients from model 1. And I'll hit enter. And now we see under values in our environment pane, we have coefs1, and there are 3 values in it, a minus 49.549, which is the coefficient of our intercept, or B naught. The second value is 0.355, matches with our coefficient for marketing, and our final value is 1.015, which matches our coefficient for employed. So now that we've created our coefficients, we can figure out how many applicants to expect if we have a budget of $80,000 for marketing and 50% of our graduates are employed within 3 months of graduation. So to do that, I'm going to create another object, and I'm going to call it applicants 8050, because we're looking at our number of applicants, and we have $80,000 in marketing, and 50% of our graduates are employed within 3 months of graduation. So we're going to use coefs1 and then we want to use the number in the first position, which is our intercept, plus coefs 1, and then in the box brackets 2, because now we want to use the value in the second position. And I'm going to multiply this by 80 because that is the marketing budget that we have. And then coefs 1 again, and 3 in the box brackets because that is the value we want to call in. We want our coefficient for employed, and 50% of our students are employed within 3 months of graduation, so that value is going to be 50. And now we see applicants 8050 is a value that now exists in our environment. And now we'll do the same thing, but we're going to adjust the employment numbers just a little bit. Just hit the up arrow to recall that last bit of code, and I'm just making those 2 modifications. Now I'm calling this item applicants 8080, and the coefficient, the value we're multiplying our third coefficient by is now 80 as opposed to 50. I'll hit enter, and we see that object now also has been created in our environment, and it is a number that is twice the number from our first one. Well, isn't that just interesting? But maybe there's a relationship between the marketing of the program and the percent of students who are employed. If it is a program that markets prolifically and is very, very broadly seen, maybe employers recognize it more, and I don't know, maybe they subconsciously favor those who graduated from this very, very well-publicized program. So, given that that might be a reasonable argument to make, it might also be reasonable for us to try a model with these 2 variables set up as an interaction. So we're going to create our interaction term. We're going to call it interaction. And we're multiplying marketing by employed. And now I have my interaction item in my environment pane here, and we see that I have 80 observations, and that means there's 1 for every single observation in our existing marketing underscore MSA data file. So we're ready to rock with that. So now we can create model 2. Model 2 is going to be another linear regression model where we're looking at applicants, and then we're using the tilde because we're now going from our dependent to our independent variable, then marketing plus employed plus interaction. That is now also a thing that exists. We can use the summary function just to take a peek at what it looks like. And we see that we have a pretty different outcome, that the significance of our marketing variable is now not really significant, and both employed and interaction are weakly significant. So we might want to compare these side by side because this may not have been the outcome you were anticipating or I was anticipating. I like to use the Stargazer package when I'm comparing models side by side, so we're going to add Stargazer to the working library. Now that I've done that, I can use the Stargazer function. Stargazer, model 1, model 2, and then the type is going to be text. You can do HTML. There are many different types you can use to create tables using Stargazer. So here I now have my results comparing the 2 models side by side, and we can see what different values we get. And we find that both models are significant, and we find that the adjusted R squared is even slightly better in our model with the interaction term, although it's very slight. So this model might give you a little bit of food for thought, and you may want to go back and look at the text and see what it means when adding an interaction term really shifts the significance of variables like that. It could help you interpret and maybe decide for certain what you think the best model really is. Because even if both models are statistically significant, depending on what you're looking for, you can usually determine which one is best. But let's see what our coefficients look like. Let's see what the result looks like when we are trying to estimate the number of applications we'll get if we spend $80,000 and have 50% of our applicants employed within 3 months of graduation. So we're going to create another vector, coefs2, and these are going to be the coefficients from model 2. If I can type. There we go. And now I'll go ahead and calculate these values. And with the interaction term though, we are multiplying the value we have for marketing and employed, and we're multiplying that by our interaction term. And we can actually use R just like a calculator. So we can multiply 80 by 50, and it gives us 4,000. So now we know what to plug into our equation. So now we're going to create a value. I'm going to call it int 8050. So this is our model with our interaction term. But again, we have $80,000 of marketing expenditures or budget available to us, and half of our students have a position within 3 months of graduation. So now we're pulling from coefs2. We want the coefficient of the first position, which is our intercept. That one's all by itself. Now we want coefs2 position 2, and we're going to multiply that by 80 because that's our marketing budget. Coefs2, now in the third position, we're going to multiply this by 50 because that's our number of graduates. And then because of the interaction term, we have a fourth coefficient, so we will call on coefs2 position 4, and we multiply this one by 4,000 because that's what 80 times 50 is, and our interaction term is marketing multiplied by employed. And now we see for int 8050, our predicted value is 33, and we see that up here in our under the values item in our global environment pane. Comparing that just off the cuff to applicants 8050, that's a modest increase. So let's try int 8080. Well, first let's multiply 80 times 80 so we know what to put in for that to multiply our coefficient in the fourth position by. 6,400. All right, game on. I'm going to hit the up arrow twice, and that's going to take me to the code that I used to create int 8050. And I'm just going to modify this. It's now going to be int 8080, and then I'm changing the value that my coefficient for employed is. I'm changing that from 50 to 80, and I'm changing the value I multiply the interaction term by from 4,000 to 6,400. And we see that value up in our environment pane is 58.6, which is a little bit lower than the applicant's 8080 value we got from our original model. And then with this, if we want to compare these values neat and tidy in a table, well, there's some code for that. And I've demonstrated it in detail in some of the other videos. So I'm just going to copy the code right in, and we'll see what it looks like. So in this case, because I copied code from Word, there are some errors, and what happens is that the quotation marks in Word are formatted a little bit differently than the quotation marks in R. So when we try to copy things in from other programs, it's really important to look and see if there are any things that are unusual or different. And if you zoom in really, really closely, you'll see that the quotation marks on model 1 here look a little bit different than quotation marks that you might more normally see in R. So I'm going to copy this code back in. And I'm going to change these quotation marks, and you're going to see that they look a little bit different. So they're not quite as curly. And this is one of the reasons why it's really handy to develop skills with creating R files and RMD files, that you don't run into these formatting issues when you work in a text editor or work within the R environment itself. Now that's what I wanted to see from my table, where I have my first column is the results from Model 1, and the second column is the results from Model 2, and then my first row indicates 50% employment, and my second row indicates 80% employment. So here now I can look at these values side by side,